All right. Lesson 2.1, which is on reciprocal functions. Reciprocal functions are a special type of rational functions, which is what we're talking about in this unit. And hopefully, it says for the 3-minute review, you've tried number 1 or example 1 on a handout in class. So hopefully you've tried that. If you haven't, you should do that, or at least as most of it as you can. I shall take it up here shortly. Pause if you need to. In A, we're asked to graph the two functions f at x equals x and g at x equals 1 over x. So I did that in blue and in red, as you can see. The function g at x is called the reciprocal function of f because x and 1 over x are reciprocals, i.e. g at x is 1 over f at x. That's what they mean to be reciprocal. So what does it mean for two quantities to be reciprocals? In sort of lay terms, in the layman's terms, we could say they're flips of each other. To get one, you just flip the other one, right? Technically, what it means, two quantities are reciprocals if their product is equal to 1. So, for instance, here, when this is true, mathematically, if this is true, if I take this quantity and multiply by this quantity and I get 1, that's what it means for them to be reciprocals. That's sort of more technical than saying they're flips of each other, even though that's the way we think of it. All right, and so we're supposed to refer to this graph and fill in the blanks. Now I'm going to zoom out a little bit here just so I can see the graph and fill in the blanks at the same time. Will that work? That'll work. So if f at x equals 0, so this is when the blue one is equal to 0, the g at x, what happens there? Well, g at x is undefined there, isn't it? That's the 1 over x. G at x is undefined. We could say that it has a vertical asymptote, right? If f at x is positive, then the reciprocal function g at x, well, look at right here is where f at x is positive. Notice that g at x is also positive. And that makes sense in our relationship here, right? If this is positive and we get a positive answer, well, g has to be positive as well. So when f is negative, g at x is negative. And that's true. We're just looking at this one example, but the idea here is we're going to build up evidence for reciprocal functions in general. When the graphs touch, that is, when f at x equals g at x, well, what happens? Well, it's this point here. In fact, the idea, it's when I flip the output, right? If I flip the y value and it doesn't change. So when f at x and g at x are equal, it's when y equals 1. Or, notice when I flip -1 as well. And this is what I'll call stationary points, that when we take the reciprocal, they don't move, right? When I flip y equals 1, it ends up with 1, and when y equals -1, it ends up with -1. It doesn't move. All right, here we go. Let's keep going. When f at x is increasing, the reciprocal function is, okay, so notice that it just happens that the function we picked, f at x equals x, because it's one that we know, it's always increasing. But what's going on with g at x? It's going down. Even over here, it's going downhill, going downhill, going downhill, 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 downhill. So when f at x is increasing, then the reciprocal is decreasing. We saw that on the graph. But think of it here, right? F at x is going up, but I have to get a product of 1. Oh, the dog's barking. Somebody might be at the door here. Let me just check it out. No, no one at the door. The dog's just nuts. Where was I? Oh, yes. I have two things, and their product is 1. This one's going up. What has to be happening to this one? It has to be going down, right? for them to have a constant product. So let's take a guess. When f at x is decreasing, then the reciprocal function is, so if this is going down, that one must be going up, right? Hopefully that makes sense to you. When f at x is close to 0, a small number, then g at x, well, so I think of the blue one getting close to 0. What's happening to the red one? Well, it's far away from 0. When f at x is close to 0, g at x is far from 0. Far, let me clean that up. And we could think of that as the asymptote as well, right? We could think of it as approaching infinity, right? As x gets close to 0, the blue one gets close to 0, the red one gets way far away from 0, positive infinity. But notice if I think of it on this side, if the graph is getting close to 0 and I'm flipping that, it could be, if it's a negative, right, because it's got a reciprocal graphs are both the same sign as far as negative, then it'd be negative infinity. So I'm going to say it's approaching positive infinity, or depending on whether the graph is approaching 0 from a negative value, it could be negative infinity, right? So when f at x is close to 0, then g at x is far from 0. It's approaching infinity. Now, think of it the other way. If f at x, the blue one, is far away from 0, then what's happening to its reciprocal? So I think of f at x is approaching infinity. It's going off to anywhere, right, to infinity. What's happening to g at x? Well, it's getting close to 0. And that makes sense, right? If I think of f at x being very, 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 very big, and I'm multiplying by some number to get 1, that means that's got to be very, 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 very small to counteract that. And notice that same thing that I could think of it as, if f at x is going to negative infinity, it's getting close to 0, but being negative. And we'll talk more about these. So this recipe is going to allow us to draw graphs of functions, reciprocal functions, that are like this. So how am I doing for time here? I'll do the first one on this in this video, and then we'll go into part 2. So for instance, what I'm going to do is I'm going to graph f at x equals 2x minus 4 first. I should have set up my scale here to not waste time, but you're all right with that, I'm sure. Here we go. What kind of scale should I use here? I'm just going to keep it nice. Each square is worth 1, so this is going to be, whoops. Well, I'm going to zoom back in. That's what's going on. I wonder why it was so small. There we go. So f at x is 2x minus 4. And then if this is 2 and 4, 2 and 4, this is a line with the slope is 2 and the y-intercept is -4, so I can graph that quickly. Color here. -1, -2, -3, -4, and then the slope up 2, right 1, up 2, right 1, up 2, right 1, that's the slope. And then I'm going to graph this. Now notice, this isn't the function I want, right? This is the reciprocal. Well, why does that, how does that help me? Well, just hang on. This is well, what I'm going to do is I'm going to go through these procedures and think about what the red one must look like, which is the reciprocal. So what's it going to look like? Well, first of all, I know all of these things here. For instance, Where f at x is 0, the reciprocal function is undefined. So where the blue one is 0, the red one is undefined. Right there. Right? So that means there's going to be an asymptote right there. A vertical asymptote. So I'm going to put a vertical asymptote right there. Dandy, what's the next thing? Next thing is, on the recipe, if f at x is positive, then the reciprocal function is positive, and same thing for negative. So where the blue one's positive, the red one's going to be positive. So the red one's going to be positive here and negative down here. You can almost picture what it's going to look like, right? Well, let's keep just following the recipe. The graphs touch when y equals 1 or y equals -1. So that means where y equals 1, I'm going to have a red point. So there's y equals 1 right there. I'm going to put a big fat dot there at -1 to show where the graphs are stationary. And that makes sense, right? Where this is 1, where the blue graph is 1, and I flip it, when you flip 1, it stays 1. And that's why we think of y being 1 and -1 as stationary points. So I'm going to put those big fat dots on there and then follow the recipe. What's the next step in the recipe? When f at x is increasing, the reciprocal function is decreasing. So this one is always increasing, right? It's always going up, so that means the red one must always be going down. And you can picture this now. We could fill in the blanks. But let's just go through the recipe and see what else it tells us. When f at x is close to 0, g at x is far from 0. When f at x, the blue one is close to 0, the red one is far from 0. So it means when the blue one's getting close to being 0, that this one's going to be far from 0. Right? Similarly, when the blue one is far from 0, the red one is close to 0. And that gives us that nice shape that we're used to. And it's very steep compared to the last one, perhaps. And maybe I should have fixed my scale. Again, and notice, blue's increasing, red's decreasing. Blue's positive, red's positive. All of these things make sense and match up. When the blue one's close to 0, the red one's far from 0. So it gives me this vertical asymptote. When the blue one's far from 0, the red one's close to 0. And there's my graph. Now there might be one other point that we want, and that's that one right there, perhaps the y-intercept. Well, what's the y-intercept here? The y-intercept there is 4, right? And then if I want to take the reciprocal of that's going to be flip of -4 is -1/4. And notice that's exactly the same thing as if I were to just fill in x equals 0, and I would get -1/4 as the y-intercept. All right, I'm going to pick up example 2 example B and C and part 2. I guess it's example 3 in part 2 of this video.